Okay, everyone. Welcome to the 3D printed, welcome everyone to the Strength of 3D Printed Electronics webinar. Thanks everyone for signing up. We hope everyone is safe and healthy and trying to turn lemons into lemonade in this situation. We're excited to get a great turnout. I just have a couple of ground rules. We're going to take all questions at the end. We should have about 20 minutes for questions. All questions will be in the chat feature on the platform. The audience will be muted through the whole time of this webinar. You can address a particular question to a particular speaker if you like, or to the whole panel. Now, my colleague, LJ Holmes, will introduce the first speaker.
Thanks, John. I appreciate it. So we've got a great lineup today. Our first speaker is Mr. James Zannino. Jim has degrees in chemical engineering and an MBA from New Jersey Institute of Technology. Jim's also a co-founder of the U.S. Army's Additive Manufacturing Community of Practice. That's an organization consisting of every U.S. Army principal investigator with a portfolio in additive manufacturing. Jim is the AM principal at the U.S. Army CCDC Armament Center at Picatinny Arsenal. And while his position as AM principal requires him to be informed on all armament-related additive manufacturing work, he's been a large proponent of multi-material, multi-technology, 3D printed electronics for quite some time. So it's my pleasure to introduce a longtime friend and colleague, Mr. Jim Zannino. Go ahead, Jim.
Thanks, LJ. So I'm going to talk a little bit about transformative manufacturing techniques for novel printed armament technologies. So when we say transformative manufacturing, disruptive change with unique technologies, but transformative is more than just printing or AM. It brings in all the different major manufacturing or advanced manufacturing technologies, but it includes the fabrication, the advanced materials and processes, and the inspection and testing and how those all work together. And it's really how we're transforming how the Department of Defense and the organic industrial base are working to provide both modernization and readiness objectives. So transformative manufacturing allows digital integration across the echelons and includes in situ monitoring, digital engineering that can be updated in real time to meet operational needs. So the Army, under the Army Futures Command, has, they call them the 31+3, but basically 31 signature efforts, and transformative manufacturing touches upon all these major programs, and it's how the Army is really going to get itself to the future level. And by transforming all these technologies and using these new advanced manufacturing approaches, we can enhance and enable technologies to meet these priorities. It's up to us, DoD, industry, and academia, to work together, use best practices, and bring the Army into the prepared for the future battles. The map is a quick snapshot of where all the advanced manufacturing capabilities sit across the Army. That includes the Army Futures Command, which the Combat Capabilities Development Command is part of, and I'm at the Armament Center, but also all the Army's organic industrial base sites, such as Rock Island Arsenal's Joint Manufacturing Center of Excellence for AM, Army Medical, and the Army Corps of Engineers. At the Armament Center, we have full advanced research all the way through demilitarization, so full life cycle responsibility, from design to testing, qualification, certification, the whole aspect. And we work on 4 of the 5 major AM domains. So you have printed electronics, metals, polymers, energetics, and the other domain is chem bio food. But 4 of those domains are done at the Armament Center, and truly integrating and using hybrid manufacturing techniques to integrate electronics to make 3D electronics into structures is one of the main areas we're really focusing on. So of that, the PEAM Center for Innovation is something that we've been working on for several years, but it's a combination of facilities at the Armament Center and across Army CCDC sites that bring this capability to print electronics, energetics, materials, and sensors with new and innovative products and methods. And it's really the backbone on how we do 3D electronics. So some of the current systems and subsystem efforts we're focusing on is using 3D printing for electronics, embedding electronics, hybrid additive manufacturing for munitions and power sources, new capabilities in ammunition and warheads to do increased lethality and better performance, integrating stuff on for soldier systems, armaments, munitions, and threat detection, using new technologies and techniques to help us better protect our current system technology. We do a lot of instrumentation and sensing for training and simulation, sensors for systems health monitoring, prognostics, and diagnostics. And by system, we mean the entire system. So the soldier is a system, vehicles are a system, the bullet's a system, the gun. So big picture, the armament center, how do we enable a bullet and make it a smarter round? And how does that round communicate to the weapon and the weapon communicate back to the soldier or vehicle it's connected to? And how does that information get collected so we can actually make smart on-field, real-time battlefield decisions? And then we do a lot of stuff for integrating manned and unmanned teaming and remote weapon systems and unmanned systems. And we do a lot of work for special projects and special operation forces. So some of the current thrusts we've been focusing on for 3D electronics is for armaments and munitions. So one example is working on a novel power source and a fuse to modernize the M67 IM grenade and the fuse for it to make it safer and more reliable, but also giving it increased performance. And with that, you can actually add more capability into the existing form factor, but you don't want to completely change everything because a lot of time and money goes into training and setting up the production lines and managing that full life cycle. So if we can use these advanced techniques, 3D printed electronics, and integrate those into existing systems to update and modernize them, that's really what we're talking about when we're doing transformative manufacturing. So for munitions and warheads, integration of electronics and energetics together, working on fuse and initiation systems, antennas and guidance packages, and then actually working on stuff to help with threat detection, counter stuff, like arrays, frequency selective surfaces, radar subsystems, fully printing munitions, integrating munitions into other components, and then working on UAS and counter UASs. So some of the major programs is extended range cannon artillery and enhanced PNT that support long range precision fires. And under soldier lethality, hand and place munitions, next generation hand grenade, and the enhanced 40mm rounds, all using 3D electronics and 3D structures to enable the future warfighting capability. Another area that we're doing a lot of work on is power solutions. So you have energy harvesters, printed capacitors, printed batteries, primary, secondary batteries, different biodegradable batteries, photovoltaics. And then the applications of those, as you can see from all these examples, is across the board. But how do we power a Picatinny rail and integrating power into existing structures? How do we make dynamic grips and embed sensors and electronics and power that? So these systems are really 3D electronics that take advantage of existing real estate and don't add that much weight or size, but actually integrate into the system so it's a seamless integration. So munition batteries, integrated power for munition systems, soldier systems, weapon systems, and using all those different technologies and capabilities. The other area where we have a current thrust is asset monitoring, prognostics, and diagnostics. So this is munitions health monitoring and tracking, like the R-Rapids device, where we're trying to use flex hybrid electronics and 3D printed structures to take the sensors that are usually just on the cover, but embed those down inside where the munition is in the sealed container, so we can actually get real-time information of what's going on, how many times is it dropped, banged, overheated, what are the off-gassing, to really give prognostic and diagnostic capabilities to our munitions and assets. We also do this for wearables and embedded sensors. So embedding systems like active fire control, embedding prognostics and diagnostics into the weapon systems, doing systems monitoring, and a lot of soldier wearables and stuff like that, and integrating it, as well as munition systems, keeping track of what's going on with our guns, bullets, and weapons. So using stuff like RF tracking, RFID tags, smart tags. And the one thing to remember is a lot of this stuff is going to be integrated with, onto, or near explosives and energetics. So we have to make sure everything meets all the hero safe requirements, being able safely to work, because we spent a long time in the Army developing RF initiation systems for our systems, and now we're going to take RFID tags and try to put them on our devices. So that has to be thought about very well. So we are working in the right frequencies, the right bandwidths, and that there's no leakage or signal leakage that could affect ammunition or affect the fuse.
Hey, Jim, you got about 1:45.
Yep. And then another area is operationalizing AM and flex hybrid electronics. So this is how we take what's really being done in the lab and how we get it out to the front lines or use it to get new systems out to the front lines. So we do a lot of work with unmanned systems integration, embedding electronics and structures into 3D structures or appliques onto stuff. We also do this to help develop special testing and analysis, embedding sensors and electronics into existing test structures and test fixtures so we can get better testing and instrumentation, and then getting as much of this out to the warfighter as possible. So electronics fabrication, repair at the point of need, systems like the RFAB, the REEF, the FAME system, and getting these capabilities to help reduce weight and help the warfighter. One thing we're always doing at the Army's Futures Command, and especially at CCDC Armament Center, is we're looking for strategic partners, transitioning ideas, getting ideas from industry and academia, and enabling this acceleration and transition. We have a lot of active cooperative research and development agreements, educational and partnership agreements, and we're constantly trying to work together to build the best thing and really be a whole family that takes all these manufacturing technologies across the US and integrates them for DoD applications. In summary, through manufacturing, advanced capabilities can be added to our current systems. Until we can print everything, hybrid fabrication is required. A lot of us say print what you can, place what you can't. By partnering in transition with the other services and OIB, we can support our warfighters at home and abroad. And this will result in new and modernized weapons to help meet readiness and modernization objectives.
Yeah, thanks a lot, Jim. I appreciate that. Perfect timing. John, I'm going to turn it over to you.
Okay, thanks, LJ. It's my pleasure to introduce Ken Church. Ken holds a PhD in electrical engineering and is the CEO of Enscript and Cyperio, its research arm, which are both located here in the United States in Orlando, Florida. In my view, as an observer of the industry, Ken and his companies pioneered 3D manufacturing of printed circuit structures using Enscript's factory and a tool. So it's my pleasure to introduce Ken Church. Ken?
Okay, thanks so much, John. Big shout out, by the way, to LJ and Brandon for making this happen. I think you guys put something together on very short notice and made it pretty amazing. So I appreciate that very much. So I want to talk just a little bit about what, at least in my mind, is what is electronic packaging. So printing for electronics now and in the future. And so as I start looking at it, I look at the evolution of electronic packaging. And I think one of the best examples that I've seen is the evolution of the smartphone. And so if you look on the upper left-hand corner there, you'll see sort of the first mobile phone. And then as it transitions over time to what we have today is a very sophisticated piece. And what's interesting about this is the phone on the far left, it did, well, all it did was talk. And if you remember that phone, you're probably old and rich. And so as it went over time, you can see a lot of things happen. And I like that list on the right, and there's a very long list. It's not of things, of sensors and cameras, things in it. It's things that it replaced, from GPS navigation to camcorders to alarm clocks, calculators, even such things as barcode scanners. The list continues to grow, and it was very exciting. But so let's take it apart and look at it from an electronic point of view. And that's what this picture in the middle is. And so when you take it apart, basically this thing is full of, well, it's full of glue and solder and lots of stuff. And that's electronics. And then if you look at the bullet points over to the left hand over here, if you see that little bullet point here, that's not a bullet point, that's an earbud. And this earbud does what this thing does. It talks. And so you can listen. And this is also full of glue and solder and lots of stuff, but just at a much, much smaller scale. And that's really where it went. So electronics is going to a much, much smaller scale. And this is where precision really became important. So as electronics today, where does printing happen today? Well, it happens right here in printed adhesives. That's an important concept to get a hold of. It happens in printed solders, also an important. So what you want to do is make those smaller. And so the printed adhesives, you can see those are less than 100 micron dots, and you want that consistent. Printed solder, again, less than 100 micron dots, and you want that consistent. And then it's moved to printed antennas. Printed antennas are interesting, and most people are familiar with LDS, a laser direct structuring. And so you have a special plastic, and wherever you pattern with that laser, you then go back and you electroplate that copper pattern on that. The advantage of printing this, on the other hand, has a couple. One, you can now change substrates. Whatever substrate you want to do, you can then print on, and that it gives you some advantages, but it also can give you an advantage in cost. So printed antennas are also moving in a direction and becoming very real as well. And then also moving toward printed conductors, and the printed conductors become very important as they start doing such things as printing directly to the pads of bare die. And the idea behind that, and this is happening today, it's low profile, but it's also a more rugged approach. And so this has some benefactors in that as well. And then we start looking at materials. And so all of these things that we're talking about right now are about printing. And so printing on existing electronics, but what about next generation? Where's it going? And so the upper left-hand corner, that is iron-filled silicone, and then unfilled silicone, and then patterned back and forth. And so we can transition and make some extra features if you want. The lower right-hand corner is interesting, and we talk a lot about this, but we haven't done a lot of this. And so I think this is coming, and that is gradients. 3 materials, an infinite number of colors, and from 3 materials. So what can we do with this? And that's what's really interesting. So we can do some loading on the materials through nano and micro, or we can also change material properties through macro and milli patterning. And that is also sort of a 3D process. And where does it lead to? Via filling, printed resistors, sensors, antennas, a doubly curved. And doubly curved to me is like a basketball. That is doubly curved, a half a basketball. You know, a cylinder is a tube, but topographical printing, I'm not talking about maps. I'm really talking about whatever you're printing on has some sharp, you know, dips and valleys and peaks. And how do I get electronics on that? The only way we do that today is through printing. And so we have that advantage. So we have a toolbox of things, and those toolboxes of materials and material placement are important. And this is how we do it. So we take a bunch of these devices, these tools, from micro dispensing to 3D printing, pick and place, precision, and we put those all on a single tool plate. And we called this the pentahead. And then we put this inside a single system. And that system then allowed us to do multi-material, multi-process. And so now our toolbox is becoming full. And what can we do with the toolbox? Well, as we print, one of the things we should do is pay very close attention to what we're printing. And so I want to give a shout out to NASA here. NASA had the idea that the people on the space station were kind of busy and didn't have time to print, reprint. When you print 1,000 layers and a layer goes bad, they wanted to know what happens in each layer. And so layer by layer, we can print, scan, and go to get a full report on every layer. This is very important. The next step of really where manufacturing is going to happen. And sort of the next step after that is print, scan, and then repair. And that's going to be very interesting. And right here, this is sort of an example of where we're going, or where we've been, I think is a good way to say that as well. In the upper right-hand corner, this was done by the Air Force. So I want to give them a shout out. So we worked with them, and this is 7 RF functional layers inside that. And each one of those little quadrants is an antenna element. And it's not just the antenna element, but it's the RF structure that sits above that and permeates through that to comprise that antenna array. That is a complicated, very challenging print, and the Air Force has been determined to do that and continues to do that. So we're increasing the number of elements. So we're moving to an 8x8 and even curved. I also want to look at what's on the upper left in that heart. And for those of you who just love 3D printed electronics, yes, I did say that. For those of you who love that, we give you this, and here's really where this goes. It's not the fact that it has a cool shape to it. It's the fact that this thing, we think Guinness should call us. The Guinness Book of World Records should call us. This heart was printed over 5 years ago and has been running nonstop for 5 years. It has never, ever turned off. We're not sure what that means exactly, except, well, it's still running. It was 3D printed, so that's got to mean something. And so what I want to do is I'd really like to give a shout out to the Army here. This has been interesting and fun to work with our Army friends. And so what Army is just absolutely bent on doing is making virtual reality real. And so this is really where we've been working on that. So taking some kind of a cylindrical shape and put electronics in a cylindrical shape. And this is really what we talk about, bringing virtual reality to life. These are things that are really happening today. These proofs are moving along. What has not moved as far along, and we have a lot of work to do, is the hardening of this. And so we don't understand exactly how this is going to come out, and that becomes really important. So what's the impact of doing something like this? I think the impact is predictably unpredictable. And it's really important to say that because, you know, what about, oh, I don't know, the digital phone? Where was the digital phone going to go when that thing started? I'm sure you're looking back at it. If you're Kodak, you wish you had that one to do again, because that turned out to be an amazing impact and you could not see it coming. So
Ken, you have about 2 minutes.
A shape like this, the fact is much of it will be unpredictable, but again, hats off to Army. They're pretty bent on bending things. So where have we been and where are we going? We've been to the desert on a horse with no name, and we went to space, the final frontier. And so if you look at the upper left-hand corner, the wheels are not ours, the buggy is not ours, but that little gray box in the back of that, that is an in-rugged printer. And that was someplace over in Africa printing. And why is it over there? Well, I can't answer that because I probably didn't really know. And over on the upper right-hand corner, it has gone to space and it's on the International Space Station. So we are truly going places and we're printing where you wouldn't normally print. But I want to go to the lower left. We're also industrial. We are on the manufacturing floor right now, working on printed, not printed electronics so much as it is what we're really talking about, electronic packaging. In electronic packaging, we are running 23/7, 365. In other words, this is more real than we know. And sometimes we just do not understand it because we do not recognize it. So where are we at? We're in industrial parks today. Where are we going? We think we're going to neighborhoods. You know, how real is that going to be? What a super great question, but that is the intent. So when we start looking at our partners at NASA, and we start looking at our partners at Air Force and our partners with Army, DARPA, all of those people, when we start looking at that, these are the people who are moving and shaking things and getting us out into places that, where electronics does not currently exist. Here's where I'd really like to look at, because people always ask this. They say, where exactly are we and where are we going to be in 5 years and where are we going to be in 10 years? I like to look at it this way. You know, we have a list of things, but today, you know, I have a pair of these Oakleys and today
Time's up, Ken. Time's up.
Thanks, sir. They reduce sunlight and they make me look cool. And that's great. But tomorrow, it's going to be a very long list of what these things do, and unpredictable of where it's really going to be. So today, where are we at now? I think now we're definitely printing antennas. We are now definitely printing sensors. They're more in prototype stage, but they're starting to move in larger volume. Within 5 years, we'll be printing printed circuit cylinders. And I call this 2.75D. It's still layer by layer, and maybe we're turning some things, but true 3D printed electronics is coming in the future. And at that point, we will make some amazing things that even our minds who are leading this thing are going to be baffled by where this goes. And we appreciate everybody who's here today, and we appreciate your time. I'll give it back to John.
Okay, LJ, I'll turn it over to you. Thanks, Ken. Thanks very much. I'll turn it over to you, LJ, for the next introduction.
Wonderful. Thanks a lot, gentlemen. Our next speaker is Dr. Amanda Strand. Amanda scored her PhD in materials engineering from the University of Dayton. Amanda developed and was the principal investigator for the Flexible Electronics and General Ordnance Manufacturing Program in the Air Force, otherwise known as FLEGO-MAN. That was the first deep investigation of multi-material electronics printing in the Air Force. Dr. Strand is now the senior engineer and group leader for resilient hybrid additive development at AFRL and Eglin Air Force Base. And it's my pleasure to introduce my friend Amanda Strand.
Great. Well, hello, everyone. Thank you, everyone, for inviting me. I just want to share my screen now. Let's go here. All right. Does everyone see my screen? All right. Can you guys see my screen?
Yeah, everybody can see your screen. Make sure to
Alright.
hit slideshow.
All right.
Right there, perfect.
All right. So let me first give a shout out to my team members. They're listed here on the slide. Edwin Elston is one of our senior engineers. Clayton Neff is our current postdoc, and Chris Kimbrough is our lab tech. So we're a small team, but we started about 5-6 years ago, really focusing on survivability of printed hybrid electronics. So some parts are printed, some parts are commercial off the shelf. And that's the title of this talk. Because we are Air Force, we work with a lot of other, the services, Army, the Navy, and other AFRL groups. So we're part of the Air Force Research Lab. And I put this slide up just to show you that as we look at survivability and resilience, we're really looking at electrical, mechanical, and thermal properties. And that's for us primarily a high G environment or high impact environment. And starting here at first, we'll look at materials and designs, spend a lot of time with different companies and different chemists to look at what really makes the best materials. We don't do that in our lab, but that's a huge collaboration that we work on. Most of what we do in our lab is the proof of concept. So once we have the designs and the materials, we will start to combine those to basically demonstrate that they can handle high current, high impact, different high temperature and things like that. And as Ken said and everyone else, you know, printed antennas has been a pretty popular area, as well as just different ways to replace potting in more elegant ways, more sophisticated or complex designs through 3D printing the structures. And so we'll title that Innovative Packaging. And then the final section on here is more towards the applications. So just to give you a few examples, we've worked in Phlego-Man on a printed capacitor, some different RFIDs, again, flexible or other printed antennas that have actually been implemented on the Reaper. And here's another example of flexible. So we don't necessarily work on flexible, but conformal is one area. And you'll see some examples of that later. Wanted to give you a preview of what technology, printing technology is in our lab and what where we intend to go by the end of the talk. But we do have traditional circuit board printing software. We use a lot of SolidWorks and Autodesk as far as our software goes. And we have some plastic printers. We don't use those a whole lot for our electronics. It's more form and fit check and prototyping, but we have a MakerBot in a form lab. The primary machine that we use is what Ken just described from his company is Inscript. And so the majority of our talk will be how we've outfitted and are using the Inscript. We have a larger scale printer called the Beast. We had a Voxel 8, which is no longer being sold. I guess it's out, that company's out of business. And a high temperature printer that we haven't set up yet for polyether ether ketone, otherwise known as PEEK, high temperature polymer, and a lot of other accessories. So the lab's grown and we continue to outfit our Inscript.
Hey, Amanda, real quick, I'm sorry. Can you hit the slideshow button on the bottom right? It's still not showing, like slideshow mode.
Oh, sorry about that.
No, it's
Okay.
okay. Thanks so much.
All right, so we're in slideshow mode. Here we go. This is one of our early papers. And again, I wanted to toss this out there because design and testing go hand in hand. You really can't understand your results unless you focus on why you chose your designs. So we have designs for electrical testing, designs for antenna testing, and you'll notice both of those are flat. Those are planar. That's just a way for us to start our lab testing, looking at thermal cycling, high impact characterization. And we've moved to this antenna design called a Vivaldi. And that's what you'll see in the following studies is that is translated onto a conformal surface, not just the planar. So here's the reference for that paper. It's in the Journal of Additive Manufacturing. My postdoc Clayton was the first author on that. And this is another slide from that same paper. So we developed some scratch testing studies. Again, if the materials don't adhere well on a planar substrate, they're likely not to survive. It's a primary factor for surviving the high G impact. So what we found here is we compared two different DuPont inks, and we saw the second one was not as survivable as the CB028. Since that study, we've implemented quite a different variety of tools into our InScript. At one point, we implemented a lathing tool with a vacuum. So what you see on this video is basically a way to smooth the complex surface of this radome before we print on it. There's many other things that need to be done before we use this very sensitive ceramic tip for microdispensing in the InScript. So this was one step that we had, and then we started working with Autodesk to basically do the 3D simulation of the printing of that Vivaldi antenna. There's dual Vivaldis, you'll see one on each side. But one modification we made to the printer was to add a rotary stage. So basically that enables the software in the printer to rotate this radome to print on both sides of it. But I do want to say that because this is injection molded, that the surface irregularities required quite a bit of pre-processing before we did that print. And this is with the CB028 ink. So a really nice way to simulate and model the print before actually performing the operation. So I'll let this finish. But again, a great collaboration with Autodesk. And we've recently moved on to the aerosol jet printing. We have an IDS printhead in our InScript. And the reason for this is that we can get a very focused beam of material, but we can have a greater standoff distance so that we're not so sensitive to the ceramic tip potentially hitting the surface and cracking or causing other issues. So this is installed in our system. In the future, we will plan to add one of these to a 5-axis robotic arm. So I have some future slides, but one thing about the aerosol jet I'll just mention is that it's a very thin layer of materials. So we're still looking for, going back to those testing and designs, how to measure that appropriately for conductivity and other adhesion measurements with such a thin layer. How many layers should we make? You know, what's optimal thickness and things like that.
Hey, Amanda, about 1.5 minutes.
All right. So just to tantalize you with some future concepts. So these designs are 3D. We're looking at similar things with Army to embed antennas, maybe different designs like bow tie or concentric rings, a whole host of collaborators. We performed something called a tech sprint. So I'll just toss that out there. In April, we'll be doing a technology sprint on some dielectric materials for embedded electronics. And as I mentioned earlier, we're looking into the robotic arm. So we're working with Georgia Tech and the Navy to implement some AI-based materials knowledge on our printed electronics into basically a 24/7 lab of the future. So again, just toss out a few future ideas and kind of where we're at. And again, I appreciate everyone joining in and look forward to connecting. I'm sure you'll have a way to connect with all of us, and that's what I have for today. Thank you.
Thank you so much, Amanda. That was great. John, I'm gonna turn it over to you.
Oh, can't hear him.
You need to unmute. Am I unmuted? Can you hear me?
We can hear you now, John.
Okay, good. Okay, thank you.
Yep.
Thanks, LJ. It's my pleasure now to introduce Dr. Eric Handy. He's a principal scientist at SI2 Technologies, where he leads many of its printed electronics programs. He has been a principal investigator for several DoD-funded programs for polymer coatings, printed circuitry, and 3D printed antennas. He has a PhD in organic chemistry and polymer science. So I'd like to introduce Eric. Eric?
Great, thanks, John. Appreciate it. Let's share my screen now. Okay, great. Is my screen up there?
Yep, you're all good.
Okay, great. Thanks.
Uh-huh.
So appreciate the invitation to participate. We're going to talk a little bit about 3D manufacturing of RF structures, maybe along the lines of some of the things we've heard in the previous talks. So just a little background on SI2. We're a small business in the Boston area. We're entering our 18th year of business. Basically, we do RF microwave sensor solutions for DoD applications. So that involves antennas and antenna arrays, absorbers, and what have you. We work extensively with prime contractors. We have a very diverse technical staff. I mean, as John mentioned, my background's in material science. We have electrical engineers on staff, mechanical engineers. We really bring all those areas of expertise to bear on these challenges, which are clearly multidisciplinary. So just a quick look at some of the software tools that we have, most of the standard tools we have for design, CST Microwave, HFSS, let's see, SolidWorks for 3D CAD solid modeling, and that really informs some of the 3D printing work that we do. We also do some work in RF electronics. A lot of the work that we do, which I won't talk about today, just involves conventional manufacturing. What I'm going to focus on is our work with 3D printing, but the software tools are often the same. So on to the next slide, look at some of our 3D printing capabilities. So we have several multifunctional 3D printers in-house. We call them our Swiss Army knives. They are used to deposit thermoplastics using FDM. We can also deposit wet pastes, which are functional materials, which might be adhesives or electrically conductive pastes. And these same printers can also do the kinds of things we saw at the end of Amanda's presentation, where we can do milling and drilling. And ideally, we can do all of these operations in sequence without moving the part. So put some material down by FDM, put other material down by using paste dispensing, and then do trimming and modification afterward to make sure that we're meeting requirements. We're also doing some work with third parties to develop new materials. So a lot of the materials that we work with are, excuse me, commercially available, but we're doing some development of materials, both dielectrics and conductors that maybe meet our needs better than what we can simply buy from others. So these are some of the things that we think about when we get into RF design, and the RF design really involves the whole team, because though the tools and the thinking behind the design is old, the toolbox is new. So we're using new materials and new processes, and there's a lot of iteration between the RF design that we might do in HFSS and the printed parts that we might make using our multifunctional printers. So we start to think about, well, what kind of materials options do we have? For electrical conductors, we look to maximize conductivity for high power handling, for example, minimizing surface roughness for improved RF efficiency. On the dielectric side, the goal is always to minimize loss tangent. Fluoropolymers are usually an excellent choice, but sometimes difficult to print. So we often look at other options there. Another consideration is, what are the advertised properties of the printable material? And then what are the material properties like after printing? So is there alignment between the bulk properties, the literature values that we get for the materials, and their as printed properties? And if there's a delta, if there's a difference between those two, then we have to take the as printed properties, put them back into the RF design software, and make sure that we have good harmony between the design approaches that we're taking and the actual as printed materials that we're working with. A few more thoughts on material selection and process selection. We need to take account of temperature mismatches that might be present in the material choices that we make when we start combining materials. So are the temperatures that we need for sintering conductive inks, for example, compatible with the substrates that we'll be printing onto, and vice versa? I'll show a slide momentarily where we wind up going back and forth between dielectrics and conductors. When we do this well, there are a number of applications present themselves. We can look at shape conformal antennas, so antennas that follow the contours of the part. I think Ken earlier showed helmets that had antennas printed on them. We think about aerospace structures as well. So do we have an antenna that that conforms to the shape of a wing, for example, of an aircraft, or multifunctional antennas, antennas that serve several roles. So they might be playing an RF role, as you might expect, but perhaps another role as well. Perhaps there are some benefits that accrue to the platform by using multifunctional parts. So here's one example. We've also done some work with Vivaldi arrays, also known as notch arrays. This was some work funded by the Navy. The goal here was twofold. On the RF side, we needed to achieve wideband performance. And on the sort of logistical side, we needed to reduce the cost of manufacturing these. We have actually done arrays like these, and others have, using conventional manufacturing. It's a very labor-intensive, often manual process of assembling multiple PCBs together and stitching them together electrically, so you form that sort of complicated structure that you see there on the right. So our thinking was, well, using 3D printing, can we grow that structure from the ground up and not really have to get in there with our hands and slot individual circuit cards together? So stitch them together electrically, but make sure they have the right geometry. Can we grow that structure? And then to keep costs down, can we metallize that structure in a selective way using conventional plating? So it's a merger of 3D printing for the dielectric and conventional plating, hopefully the best of both worlds. And just showing here, this is that same 4x4 array, Vivaldi array, wired up and ready for testing. We put in an anechoic chamber. And when we look at the bore side pattern, then we see performance corresponding to what we expect from simulations. So this is one of our first 3D printed antenna programs, very gratifying that we achieved the success that we did. Onto a second example, switching gears a little bit now. This is a planar phased array antenna. As I'll show you in a slide or two, we also looked at a 4x4 array here. Now the challenge here was we had some funding from the Air Force to look at space-based applications. And so we needed to be 3D printing parts as space compatible materials. And we also need to be co-printing dissimilar materials, as I discussed in a slide or two ago. So thermoplastics and dielectrics, we didn't have the benefit of a plating process. So we need to be able to co-print different materials that have different demands, make different demands on the printing and have different post-processing requirements. Adding to the fun, the parts needed to be multifunctional. So we needed an array that would serve several roles and reduce cost, schedule, mass, save space on board the vehicle, which is always a requirement. Mass is always a challenge.
You have about 2 minutes, Eric.
Great, thanks. So just a quick look at what we did. This was the 4x4 array. The dielectric was space compatible Oldham. The conductor was silver paste. So if you look sort of going clockwise from top left to bottom left, this is through this montage. You can see as we print the radome first, this is out of Oldham, and then we go back and forth between printing conductor and printing dielectric to achieve the full up structure at bottom left there. Now that structure is ready for drilling vias down to the buried patches and attaching COTS connectors. So we show we can grow up this whole structure like the Vivaldi without touching the part, just going back and forth between dissimilar materials. We take the array into the chamber and we see performance that aligns very nicely with simulations. Obviously some deltas there, but we think we have a reasonable handle on what's going on there. So in conclusion, just to wrap up, we're showing that 3D printing can enable antennas that play a multifunctional role. So they can support, say, load bearing. They can play a load bearing role on a spacecraft, for example, taking up some of the structural demands of the vehicle, as well as performing an RF sense. And then as needed, we can look at combining 3D printing with conventional manufacturing to maximize design flexibility afforded by 3D printing and the performance afforded by conventional processing. So just to wrap up, I just want to thank the Air Force for the funding, particularly on the planar array work, those spacecraft arrays, and the ONR and our collaborators at University of Massachusetts at Lowell for the work on the notch arrays. And thanks for your time.
Well, thanks so much, Eric. Great presentation. I now have the pleasure of introducing Mr. Curtis Hill, who's a subject matter expert and senior materials engineer at NASA Marshall Space Flight Center in Huntsville, Alabama. He's the technical lead for the on-demand manufacturing electronics project as part of NASA's development of in-space manufacturing. And he's responsible for leading the development of printed electronics capability on the International Space Station and beyond. I'm interested in that beyond part. So Curtis?
Sorry, hold on just a second. And I'll share my screen with you. All right. Are you guys seeing my screen?
We are not.
All right, one moment then.
Yep.
All right, just one second.
Mhm.
I apologize. I'm having some trouble with this computer.
Yep.
All right. All right, let's try it one more time.
Okay.
All right.
We still
I'm
can't
not-
see your screen. If you click share screen, it should pop up with the
Yeah, I know, and it's not doing that for some reason. I apologize.
It's okay. We can see it right now, but it's now we can't.
All right, I apologize. Let me try one other thing here. Okay, here we go. All right.
Excellent.
Got
And then make sure to hit the slide. Yep.
All right, I apologize.
No worries.
First of all, let me give you a little background and overview as I go through these slides. As was mentioned, I'm the technical lead for our in-space manufacturing development of on-demand electronics. Our objective is to do a flight a demo of printed electronics in microgravity on the space station by 2024. And then we're also developing the capability for printed electronics and printing of sensors and energy storage and power generation devices out into Gateway and lunar and Mars habitats. So some of this that you'll see today are the development of technologies that are associated with those different efforts. By way of the overall project look, our in-space manufacturing is really broken up into my area, the on-demand printing of electronics, and then the other area that Ken alluded to in his talk earlier, which was, the on-demand printing of metals. We are developing capability of printing titanium and aluminum and other metals such as that. And one of the ways we're doing that is with Inscript's 3D printing capability. In terms of our electronics development, our effort is a multi-NASA center development. It includes 3 or 4 of the NASA centers. It includes some outside companies and probably 10 to 12 different academic institutions. And I'll show you some of that as we go through here. So we do some in-house development, particularly on inks. We have the capability of developing our own inks for thick film, for thin film, in a variety of different functional elements. Multi-material printers, we've got, of course, the Inscript. And our Inscript we're using sort of as a test bed for the development of our Fab Lab capability later for the space station. We swap heads in and out like the extrusion printing for inks. we're going to add a thin film inkjet capability to it. We have a laser sintering capability. We have an end milling capability. So we use it as an evaluation test bed for the processes that we're going to eventually fly on the space station. In terms of actual tech demos, our demo that we're working on for 2024 is the printing of flexible sensors. And those are going to be different types of sensors. In general, they're going to be for the monitoring of the space station environment and for the astronaut crew health monitoring. And so associated with our process development of 3D printing for the station, we're developing a variety of materials and processes for these printed sensors. And you'll see as related to that specifically, we're looking at things like solid state humidity sensors from the dielectric materials that were developed, strain sensors that are 3D printable, new component technologies where many of you are aware of these, where you can take a die, an integrated circuit die, and trim it down and print it on a flexible substrate and have a completely flexible sensing device. Structural health monitoring applications, that could be things like stress sensors for impacts on the station. It could be things as simple as temperature sensing. And then biosensors for crew health. I'll say a little bit more about that when we get in there. This year, we have a specific project that we're developing for our tech demo that will essentially be a wearable for the astronauts for crew health monitoring. And then Jim Zunino mentioned earlier energy storage and power generation. A large portion of the project that I'm working with is involved in the development of next generation technologies for power harvesting, as well as energy storage. And we've got a lot of not only in-house development going on, but a number of outside projects with universities in the area of energy and power development. Wearable sensors. This is a module on the space station right now. Currently, we're using on station wireless communications, an RFID network that's there for logistics reduction or logistics tracking, an RFID inventory control system for a lot of the things that are already on the system or on the station. And we're going to eventually take advantage of that RFID wireless network that's there for communications and power harvesting for our wearable sensors. The first project we did on this last year was the development of a little flexible board, a proof of concepts, if you will, where if you look at the upper left-hand part of this slide, you can see the CO2 monitor that the astronauts are currently wearing. It's a fairly large, bulky, unwieldy type device. And we're developing the lower left, and we even have developed a much, much smaller CO2 sensors than that at this point. But we want to have printable, on-demand printable sensors, not only that would be a lot smaller, but also that we can print in the environment that we need to do the monitoring. So the board that you see there, of course, is on Kapton polyimide. And it basically has three sections there where we can do some comparison. The left third of the board basically are commercial sensors. The middle part of the board is the microprocessor, Bluetooth low energy microprocessor, and associated electronics. And then on the right side, we have a printed thermistor, and the little white ink that you see between those leads there is actually a printed dielectric material that we developed as a humidity sensor. That
You have about 2 minutes, Curtis, about 2 minutes.
I'll rush. That we're using as a respiration sensor. Okay, Obviously, if you're an astronaut, you're under stress. And one of the things the flight surgeons have told us is they want us to develop a capability to monitor that stress. So we're developing a 3D printable cortisol biosensor, and we're doing that. This is some of the science behind it. I'll show you the project that we're doing it with in just a moment. We're also developing, as I mentioned briefly there, humidity respiration sensor that as you breathe on it, the moisture in your breath is very accurately tracked as well. All right, I want to talk a little bit about our AstroSense project as I'm closing here. We're working with NextFlex for the development of a wearable device that will eventually be our tech demo that we're going to print on station. And that's a peel and stick wearable device that will have different printed sensors on it, but the important sensor is going to be a printed cortisol sensor that will be a sweat-based harvest sensor that comes in contact with your skin. And the wireless communication that we're going to be using there is ultra low power RFID wireless that we already have, as I mentioned, infrastructure in place on the ISS. We can get 13-year battery life without obviously having to change the battery because of the low power of RFID. And then this also gives us a platform to integrate our power generation and energy storage devices on later generations of these devices. And then I'll leave you with this slide. This shows our roadmap out through Mars habitat in 2035 or so, but we're developing along the line the capability to do 3D printing, on-demand printing of electronics in a wide variety of different environments. The next one up, as I mentioned, will be the space station in 2024. And then we'll go to lunar habitat, Mars flight, and then Mars habitat. So thank you for your time. Appreciate all of you attending today.
Thank you, Curtis. You answered my question about the beyond part. Thank you. LJ, I'll turn it over to you for the next speaker.
Thanks a lot, John. I appreciate that. Just a couple things before our next speaker. I got a couple housekeeping things. A lot of folks have been asking through the chat line about contact information. So when you signed up, you gave us your email address and we will send out contact information for all the speakers. You've also asked about presentations. Since we're sharing contact information, we'll let you deal directly with the speakers and get some slide information from them. Especially since they didn't send in slides ahead of time, they're obviously presenting off their own computers. And then questions. We're going to take questions at the end of our talks. And so please, attendees, use the chat function. I see somebody already are, but some of you already are, but use the chat function at the bottom of the screen. Click on that, ask whatever questions you're feeling, and we're going to take a select few when we get done. Thanks a lot, everyone. So our next speaker is Dr. Mark Moroznik. He's a professor of electrical engineering, electrical and computer engineering at the University of Delaware, where he's also the associate department chair. Mark earned his Bachelor of Engineering in Electrical Engineering from Bradley University and his PhD in Biomedical Engineering from UPenn. At the University of Delaware, Mark has built a multidisciplinary team of scientists and engineers and a state-of-the-art facility focused on multi-material, multi-technology manufacturing of three-dimensional electronics and functional device manufacturing. And I do not joke when I say that Mark's team leads the academic world in this area. I'm proud to introduce my friend and colleague, Dr. Mark Moroznik.
Thank you so much, LJ. Let me share my screen here. All right. Thank you for inviting me. Again, I'm Mark Moroznik. I'm a professor at the University of Delaware. My background is really in radio frequency devices and systems, and I swallowed the red pill on additive manufacturing about a decade ago, and we've been trying to apply it to do things that we previously just could not do. I think as an academic, even though I wanted to do this work, you have to convince sponsors that it's important. And there's an obvious question when you talk about 3D printed electronics is why. We've gotten really good at manufacturing low-cost circuit boards at really high volumes. I think there's a number of niche areas that we've been working on, particularly for small volume, labor-intensive parts or systems. Here's where you could save lots of money and labor by automated assembly. Others have talked about point of need manufacturing, for example, up in space or at forward operating bases or places where it's hard to get things sent to you. But our real interest at the university as a research facility is really to build things that there's no other way to do. And so we've really been focusing on kind of over the horizon kind of applications. And the movie on the left is not mine, it's from a friend of mine, Raymond Rumpf at the University of Texas, El Paso. But he's been working as we have on the idea of true 3D electronics. So the question is, what could you do in electronics if you could place circuit elements wherever you wanted at whatever orientation? You could have electrical traces going in any direction you wanted. If you weren't bound anymore to planar multi-level PCB boards, what sort of functionality, what sort of savings and cost and space and energy could be accomplished with that? The other image on the right is another idea of what could you do if you could vary the material properties of either the substrate or some element arbitrarily in 3 dimensions. Neither of these two ideas have really been explored too much in the literature simply because they weren't possible to make. And now with additive manufacturing, we can realize some of these ideas, and they're outstanding research topics. I do want to talk a little bit about what the challenges are that I see getting to this level and what we're working on. And there's really 4 of them. The biggest bottleneck that we've encountered is on the material side. Doing functional electromagnetic devices at, in our case, at very high frequency, we want to get up to W-band, 110 gigahertz if we can, but certainly up to 30, 40 gigahertz. There's a big problem in getting the right materials. For example, the electrical conductivity of the inks or the paste that we can print is usually an order of magnitude below bulk properties and progressively gets worse at high frequencies. We'd love to have printable thermoplastics and resins, inks and paste with a range of electrical dielectric constants or magnetic properties. We'd like to print high temperature substrates that can stand soldering or high temperature applications or can handle extreme environments. And so there's a lot of work that needs to be done on developing these sort of materials. The other big issue with us is simply software. Circuit board analysis and layout design was meant for single or multi-level flat boards on a single material substrate, FR4. But we really want to be able to lay out boards in 3 dimensions and place electronics anywhere we want. And the software just simply doesn't exist to do that. And even if it did and could produce a Gerber file, for example, that could go in these general 3-dimensional layouts, we then have to convert that to how do we run a multi-material AM system, which might combine multiple manufacturing tools. And lastly, how do we go from 2.5D layer by layer manufacturing to true 3-dimensional printing? So I think there's been a lot of advances in this area. Professor Rumpf, for example, is developing software right now for 3D circuit layout. I know NScript has made some strides, but there's a lot of work that needs to be done on the software side. Closed loop monitoring and control. Here's a picture of one of our FDM heads when we walked in some Monday after a long print. And I'm sure those of you who have done 3D printing can sympathize with this. You either see something like this or a bird nest of polymer. The problem is 3D printing runs generally take a long time. They can be days. We've had runs that work for weeks, and there's no closed loop monitoring and control. So you leave it overnight and you come back and you wish for the best. That leads to low yields. Even though a print might take, we'll say, hours on the printer to finish, on the actual calendar, it might take much longer. So I think there's a critical need to integrate sensing, imaging, and then some closed loop control that can actually modify print parameters or clean the printer during a print to improve that. And lastly, systems. So a lot of the cool 3D electronic systems that I've seen printed are actually done on a range of different machines. And they generally, if you talk to the folks that make them, have some manual assembly involved in them. So they're moving the part from machine to machine to print either substrates or metallic elements or integrate some electronics. And this can lead to all sorts of problems, including high fabrication times, failure due to registration errors. And it's really not possible at all to use that sort of idea to do these complex 3D integrated electronics where everything is integrated into a single package. So I think what's really needed, and I think somebody else mentioned this before, is a Swiss Army knife approach, a single machine that combines a multitude of different printing modalities and materials together. So I'm going to switch gears and talk a little bit about what we have and what we use at the University of Delaware. So we are big fans of the Unscript, and they didn't pay me to say this. We have 2 machines right now, the tabletop and a 3DM 300 with a range of gizmos. And the reason we like Unscript is that they are the closest to this Army Swiss knife approach that any machines come. They have an open architecture that allows you to add your own features. So our particular Unscript, we have a range of gizmos, smart pumps that we print our own, as well as commercial inks and pastes. FDM of thermoplastics, where again, we print commercial thermoplastics and we make our own filaments where we've loaded them for high or low permittivity or magnetic properties. Pick and place of all electronics. We have a micro milling attachment that we use for smoothing surfaces, and we can get surface roughness down to a few microns. And we have a couple custom heads that we've been able to integrate. We've built our own hopper fed system. So for highly loaded polymers where it's too brittle to make filament, we do pellet printing and can integrate that directly with the Unscript. And lastly, we just purchased an IDS aerosol print head, which will integrate, and I saw the Air Force has already done that. Soon, next month, we'll actually get our 3rd Unscript, which is a 6-axis superscript, which we're really excited about. So we'll be able to get away from pure 2.5D printing and do true 3-dimensional conformal printing. This is the laboratory. So we built, I think, a pretty state-of-the-art laboratory for printed electronics. We have a range of multi-material and high-temperature polymers, ceramic printers, and a range of material development tools for making our own thermoplastic filaments, as well as other inks and pastes. This shows a few of the applications we've been working on. Our interest is really high-frequency electronics for most things. All of these devices work up to 18 gigahertz, and we've done everything from fully automated printed assemblies to conformal printed antennas. And one of the things I think we're most proud of is that we've made printed RF connectors. So I've seen a lot of designs like the one on the far left, where you have this beautiful 3D printed circuit and you have to snap on a COTS connector to it. We actually can make our own snap-on SMP connectors as well as threaded SMA connectors, and we've tested them up to 18 gigahertz and they work great. Here's an example of another sensor project we're working on with Jim Zanino, where we're doing a 3D printed chemical sensor that's all integrated into a package that can be launched with a 45mm grenade launcher. So this is a completely 3D printed sensor. All of the electronics are pick and place. There's wireless transmission and printed antennas, and it has a chemical sensor that we develop in the nose. And so you can actually launch it out, monitor some chemical activity, and have it wirelessly transmit data back to a cell phone app. And so we recently just got this working. Here's a kind of a cute project that we're working on for the Army, where they want fully printed functional robotics. So the idea is the thing on the right, where you print a robot and on its way out of the build plate, it pushes the button to print the next robot. So we're not quite there, but we can actually print some movable structures. We pick and place and integrate all the servo mechanisms, and the thing can push itself off the build plate and then move around the floor. You can see it on the bottom right, left there. We do some printing of high temperature ceramics for extreme environments. So this is a printer from a company called XJet. It's a full scale laboratory based or industrial scale printer. It prints right now zirconia and alumina. And so we've used this to print a range of high temperature electronic devices, including the photonic crystals on your left-hand side. We've made high temperature radomes with anti-reflective coatings in them. This material can withstand temperatures up to 2000 degrees C. So the integration of ceramics inside other additive manufacturing gives you really a large amount of flexibility to do 3D printing in extreme environments. And here's the last example I'll talk about. So we've been working on methods of using additive manufacturing for communications. There's a passive or beam steering is used in a range of different applications, from radar systems to satellite communications, and more recently at the high frequency 5G communications, you need some sort of beam steering at up to 30 gigahertz. So the two ways it's normally done are active phase arrays, which are very expensive, or mechanical steering a dish, which is too slow and heavy. So a third alternative is actually this idea of passive beam forming, being able to make a dielectric lens that can take a source and move it in different directions based on its location. And so instead of having a full phased array, you could just have an array of sources and a switching matrix that switch behind them. A far cheaper idea. This technology has been known for a long time, but the way of making these spatially varying structures has not been known. The dielectric constant in these lenses needs to vary continuously in 3 dimensions.
Hey, Mark, you're just about up.
Okay, I'm done?
Just one more minute.
1 more minute, great. So this shows the idea of fabricating these beam steering elements totally out of polycarbonate. So the material cost is less than $1. And then we work with a company called Deluxe Engineering, which we'll talk next, about integrating this into a product where we have the 3D printed lenses on top of an array of bow tie antennas and all the switching matrix. So we can do full active beam steering on a device that costs, instead of hundreds of thousands of dollars, you can do it for hundreds of dollars. So let me end there by thanking all the people that are actually doing the work, as well as our sponsors who are paying for it.
Thanks a lot, Mark. I really appreciate it. So keep sending in those questions. We're getting some. They're great ones. We'll ask a few of those questions when we get to the end if we have some time. If not, we'll send the questions out to our speakers and then have them respond to you. Our final speaker today is Dr. Paul Parsons. Paul received his BS in physics from the University of Delaware and his PhD in material science and engineering from the same institute. Between his degrees, he worked at the U.S. Army Research Laboratory as a material scientist for the Weapons and Materials Research Directorate. A few years ago, he co-founded Deluxe Advanced Manufacturing, where he's currently the Director of Materials Research. It's my pleasure to introduce my friend and colleague, Paul Parsons.
Thank you, LJ, and thank you, Nscript, for actually setting up this panel and giving us the opportunity as a small business to participate in this sort of discussion. All right. So in participating in this discussion about the printed electronics for RF applications, I'd like to point out that we work very closely with the University of Delaware, where they've graciously allowed us to use some of their facilities through a facilities usage agreement, and our collaborators at the Army Research Lab and Picatinny Arsenal. Going into the current additive manufacturing landscape, that's been discussed a bit from previous speakers. It's primarily dominated by single material systems, but in order to make a complex structure, particularly a circuit where you're printing dissimilar materials, one has to actually move the part out of the system to another system, re-register it, print the dissimilar material, and then continue from there. This adds time and costs to the overall production. However, with the emergence of these multi-material AM systems, this really kind of enables the fabrication of complex printed circuit and RF structures within a single system without even moving the part altogether. And a couple examples we see here are this. On the lower left is this miniature antenna array. It's very, very tiny, but it could not be made using a conventional single material system. And on the lower right is actually a dual band antenna. Kind of working with the heart of the panel itself is where we're talking about replacing printed circuit boards entirely. My personal philosophy doesn't necessarily follow that, and it's actually very closely to what Mark describes of how we can produce very high volume, low cost printed circuit boards. However, there are needs when we need to take this printed circuit board and put it in a geometry that just doesn't really fit well. With the power of multi-material additive manufacturing, we can actually conform these sorts of structures to that available space. And what I'm really going to be focusing on today is 4 topics, really. It's the simple printed circuits, the transmit and receiving components of these structures, how we get signals in and out of the structures, and of course, the materials development for these complex structures as well. For the first topic about the simple structures, this is actually one of our earlier prototypes for a printed chemical sensor. As you see, we can actually use the multi-material system, which I've neglected to mention is actually the NScript systems over at the University of Delaware, to print the conductive traces, which we connect to various components that are pick and placed. Jim very succinctly put it as print what we can and place what we can't. However, with the advent of multi-material printing, this actually allows us to put multiple layers of dissimilar materials, allowing us to slowly build up more functionality and to detect multiple material, multiple gases at the same time. And then when we start addressing the actual transmit and receiving components, we typically rely on printed antennas, which we can easily model using commercial finite element method software. We then print these, these designs using the NScripts where we can print the ground planes, the dielectrics, the conductive patches, and things like that. And we're not necessarily limited to just planar geometries. We can also print conformal, and we're very, very excited to actually use the six-axis NScript that'll be arriving, coronavirus permitting at the university for us to actually use it. And the third topic I really want to bring up is probably one of the most important topics that's really quite often overlooked, is how do we get signals in and out of these printed structures? So one of the most common failure modes is actually the interface between a connector and the printed structure itself. Using this multi-material additive manufacturing technique, we can actually, I hope you don't hear that. Multi-material printer, we can actually seamlessly integrate this type of connectors into various geometries that allow us to easily adapt and make compatible with other COTS connectors. As application space grows, we see that there are more types of connectors that are required. For instance, we have these Molex connectors on the left, which could be used for power applications. For the more RF-oriented applications, we printed the previously shown SMP connectors, but also the SMA connectors. And this actually opens up a brand new kind of avenue for how we do signal routing within these complex printed structures. We can then use these connectors, integrating them into the structures, and build our own signal routing paths within them without relying on bulky connectors or solder or anything of that nature. While we have shown actually pretty good progress using commercial materials for some of these applications, the widespread adoption of AM towards RF applications, particularly higher frequency RF applications, is severely limited by the availability of materials, not in the sense of are they physically available, but what are the properties of these materials that we can use. For instance, on the left-hand side, we're looking at the dielectric polymer filaments. They vary very differently in both mechanical and thermal performance. However, the relative permittivity of these materials is actually remarkably similar. There are applications where we require a higher permittivity or even a lower permittivity, but those materials simply do not exist. On the other hand, and probably the more important materials development process for RF applications are the conductive materials themselves. We've looked at a lot of the commercially available printable inks and pastes at high frequency on a base Rogers board. And it turns out we are very limited in the RF conductivity, especially as the frequency increases. This can be attributed to the materials not being able to fully cure and sinter on these polymer substrates, because if you do it at a high enough temperature, if you set the temperature high enough, the polymer substrates begin to warp, break down, and then decompose altogether. And we want to avoid that. So in order to increase the adoption of RF towards RF applications, we require the development of novel materials that are compatible with AM systems. We've done that with the first example by producing our own flexible, low dielectric loss tangent flexible feedstock filaments. Looking at the mean permittivity of these materials, we've developed both high dielectric materials and low dielectric materials. These sorts of composite filaments are created by introducing very specific inclusions that control volume fractions. Provided that these inclusions are very small compared to the incident wavelength, the effective properties of the composite are essentially a mixture of the properties of the polymer and the inclusions themselves.
Hey, Paul, a little less than 2 minutes, okay, buddy?
Gotcha. We can then use effective medium approximations to then predict and engineer very specific dielectric or RF properties of these composite filaments by simply controlling the volume fraction. And with that, I'd like to conclude that, wrap everything up. Multi-material AM systems really kind of enable the fabrication of complex printed circuit and RF structures within a single system. And we're not necessarily constrained to relying completely on commercial connectorization techniques. And this sort of paradigm introduces new degrees of freedom in structure design. Materials development is a very critical need where we need to tailor the AM properties of various feedstocks, but more importantly, probably targeting increasing the RF conductivity for these applications. And lastly, I'd like to leave off with how we need to be cognizant of future needs, for instance, in extreme environments such as high temperature, high Gs, and how to actually address these problems. Thank you.
Thanks a lot, Paul. That was perfect timing. You and Amanda both nailed the 10 minutes. I appreciate that. So we had some questions come in, and I'm going to switch it over to Brandon, who's going to help us with some of those questions.
Good afternoon, everyone. Thank you again for attending and watching as all of our amazing panelists answer questions that you guys may have had or showing their slides or anything like that. The first question is going to come for Curtis Hill from Christopher Booher. And the question is, what are the primary objectives for development of conductive inks and dielectric insulating inks versus options available in the market today? And I will let Curtis answer that now.
Okay, good question. I'll address dielectric inks first. The first work that I did for NASA was the development of dielectric materials for printed ultracapacitors. Our initial work in capacitive inks and dielectric materials has been in the development of ultracapacitors and supercapacitors. However, with doped dielectric materials, we do have the capability of actually printing capacitors as well, depending on the geometry that you need. So that was the real answer on dielectrics, was energy storage. But on conductors, I know there's a lot of good conductor inks that are available. I come out of a thick film background, so I'm very familiar with a wide array of conductor inks. Our development of conductors has been more for specialty type applications like aluminum, like materials for thin film inks. A lot of the thin film inks right now are high temperature curing. And since we're working on printing on like fabric films, like a Band-Aid type film that's wearable and is cured at lower temperature, we've had to redevelop some of those inks to be curable at lower temperatures. So that's, ours is really application driven. Whatever the application is, we can develop the vehicles and binders and processes to make our own inks.
Thanks so much, Curtis. So my next question is for Ken. It is from Andy Davis, and his question is, most of the pictures showed pointed traces with devices integrated in a more traditional fashion. Do you see a future where we move beyond pick and place and realize fully printed devices, for example, microchips, capacitors, etc., fully integrated within the printer? If so, what is a realistic timeline to have a production ready capability in this area? Ken?
Okay. It is certainly very traditional in how we're approaching this right now, which means that we are pointing normal to the surface and the surface is sort of flat against the earth, and we print that way. Pick and place is standard and it's slow. Printing, as you can see, can be slow. And so can we really move this to the next level where we're doing high volume manufacturing? Can we really print capacitors? Can we print inductors? The answer is yes, we do that now. If your capacitors get too big, then you want to pick and place those. We want to move from pick and place to chip shooting. And so that's one of the devices that we have on our roadmap to do. And that means that we will move literally 100 times faster in how we're placing chips. And that also gives us a chance to do something off axis as well. You don't have to just go normal to the earth, but you can start tilting and go normal to the object. So if you have a true 3D printed object and it is sitting sideways, doubly curved, then the chip head can also move itself that way. So I think, to get to where we want to be ultimately, multi-nozzle, run in parallel, multi-chip shooters run in parallel. Think about, as John would talk about it, factories inside a single system and distributing that. So the answer is we will get there. The question is when. How do you eat an elephant? Bite at a time. And that's kind of where we're at right now. So I would say in the next 5 years, I'm still going to come back and say that you're going to see some very non-traditional shapes that manufacturing industry is going to start manufacturing, and those will start moving their way into consumer electronics, certainly into some high-end medical applications, high-end aeronautics, and some of those places.
Thanks, Ken. I actually have another one back to back for you. So I have a panelist, I have an attendee by the name of Ricardo Rodriguez. And his question is, I once heard of a company called Vax Design work on printed vaccines. Can vaccines be printed? And is anyone in this group working on that?
Yeah, only that. Thank you, Ricardo, for that. So printing is maybe what you're really referring to is Vax Design. What we did do is we printed an immune system, and it was really rapid vaccine assessment. And so trying to get to that. And so basically it's a tissue engineering approach. So we are printing the biology and then letting God take over and it grows, and then injecting vaccines into that. But the advantage would be, and so we have a patent that we have filed recently on a 3D printing compounder. And so the answer is sure, why not? If you trust it well enough to try for the COVID thing, maybe a bit early on that, but we're trying to move in that direction.
Thanks so much, Ken. My next question is for Paul. So I have two questions for Paul. The first is from Subramian Ramiskin. Sorry for butchering your name, but the question is, what is some state of art in polymeric materials for the printing? What are the key issues, Paul?
Well, let's see if so some of the problems, it's going to be also addressed for specific applications. When we're talking about RF applications, we're very interested in looking at what the dielectric constant or the dielectric loss tangents of these materials are. So in the state of the art, there are companies out there that are developing and co-developing these polymer filaments. One of the things that ones that come to mind is Preperm, actually. But they are primarily addressing these specific polymers for RF applications. Once you start looking at various, other electronics, it's really kind of hard to determine what exactly is state of the art, because we're still kind of using these commercially known polymers and kind of combining these active components, these active inclusions within them. We're not actually developing a brand new polymer that kind of has these sort of attributes associated with it. So it's kind of, kind of cooking. You're combining stuff together and you're baking it. As to how they will be used in additive, we need to look at how we can incorporate these elements into these polymer composites, how we can print them, and 2 or 3 as will they actually kind of resolve the type of features that we're looking for primarily for high frequency applications.
Thanks, Paul. So the next question is from Vincent Easy. And his question is, what do you mean by novel materials that are compatible with additive manufacturing? Are looking at materials with superb mechanical properties and high conductivity? If that is what you're interested in, could you give me an example? Thanks.
Well, again, what I mean by novel materials is not necessarily a brand new example of like a polymer that has these sorts of properties associated with it. A lot of these composite materials have been actually very well studied for many years. It's just that before the advent of additive manufacturing, it wasn't really thought about in incorporating these materials into a printable form. So when I'm looking at compatible with AM, I mean primarily for RF properties, number 1. 2, the ability to print them. If you can't print them, then it doesn't make any difference how good the material is. Now, if they also have additional features that are like, for instance, very good mechanical properties in order to act as a load-bearing structure, that'd be fantastic, because we're very in tune with like multifunctional structures as well. And then, of course, when you're looking at, say, high conductivity, again, this is going to be very specific, because at the frequency of interest, a lot of these commercially available pastes that are conductive that we use actually demonstrate very high conductivity at very low frequencies. It's really only as you increase the frequency more and more that we see these sorts of downgrades, essentially, where they don't act very well.
Paul, thanks so much. So my next question is for Mark. And the question is, what is the envisioned application for fully functional 3D printed robotics? And Mark, I'll let you answer that.
Okay, I'm actually going to pass the question on to LJ, who is the PI for that project. It's an Army funded project, and I'll let him answer that.
Okay.
Thanks, Mark. I appreciate that. So my colleagues in the Army and in the other services have talked about a lot about additive manufacturing at the point of need, and to be able to reduce the logistics burden. But one of the other things that they talk about is getting the right tools in the hands of the soldier, and to be able to manufacture robotics and remote control systems that can remove the soldier from harmful situations. So in that sense, could we get a soldier or a robotic vehicle or remote system that can perform a specific mission, yet still be attritable? And to the government, attritable means it's a low enough cost that if it goes out there and gets broken, we don't have to risk somebody's life to go get it. So in this case, what we're doing is we are printing using additive manufacturing technologies, pick and place and printed electronics to print these mission specific robots that can go off and do something specific. Our first examples are robots that will help soldiers that are working on bomb disposal. So, but other robots will carry different types of sensors for biohazards and that sort of thing. So right now we're just working on being able to print them and have them roll off the printer, which you saw in that video from Mark. Hopefully more to come soon. Thanks, Mark. I appreciate that.
Thanks so much, LJ. So my next question is for Paul Parsons again. So the question is from Craig Armiento. And the question is, surface roughness of extruded dielectrics affect RF performance. How do you achieve good performance in a printed microwave connector when the dielectric extrusion methods do not have a smooth surface?
Well, how we address that is, well, for the printed connectors that we have used, we do use commercially available materials right now, so there are no inclusions in them, as I've been previously describing. The surface roughness of these parts are actually pretty low comparatively, because one, we're actually using a very fine tip end script print nozzle to make actually these parts. So the surface roughness is actually very low. Of course, these sorts of features are taken into consideration when we're performing our FEM models that allow us to actually attribute a particular surface roughness. That's kind of all we got right now. Hello? Yep, Brandon.
Yeah, thanks a lot, Paul. Looks like Brandon's mic might be off.
Yeah.
Actually, we are running out of time, but I do want to open it up to the panelists to see if they have any questions of their colleagues that are on the panel.
Hi all, can you hear me?
Yeah, thanks a lot, Brandon.
Yeah. Sorry about that. We are in the middle of a fire drill currently, so I had to run outside and I don't have the best connection currently. So if LJ or John Hornick want to look at the Q&As and finish up with the panelists, or if the panelists have any other things to say, they can finish up. Thanks, guys.
So thanks a lot. So I'm guessing, Ken, you might be having the same fire drill, but before we sign off, there were some questions about software handling multi-material printing, several of those. Is there anything coming up soon that's going to solve some of the issues with multi-material printing or with regards to software?
Ken, are you there?
Okay, I'll give this a shot. We are seriously under attack. I'm not sure what it means exactly, but I'll give this a shot. We are working on software, and the software, again, hats off to the Army folks, as they have put a lot into this, which probably means they're having some pain points. All of you guys would have pain points in this. And as we have started pressing forward with this, some great progress is being made. And we're seeing a lot of the 3D start coming together, but it's still more of a 2.5, 2.75D. And so you're building in 3D 2.5, and then you're doing conformal printing on that. That's where the software is today. What Tipper Rumpf is looking at, and what folks like LJ and their vision has been for some time, is very specifically how do we go from 2.5 to true 3D? And we are working on that sort of as more university projects, but from commercial projects, I think it's 2.5D and then conformal printing combined.
Thanks a lot, Ken. It sounds like you guys are having a really good time. I think that's
Good time.
an exciting way to end this. There are some other questions that I see that keep coming in, but we're out of time. So I think we're going to close it out. Like I said before, we're going to send out information to the attendees with panelists' contact information. And, we'll handle further questions there. We appreciate all your time. Appreciate the panelists. Thank you very much, all, especially those at NScript that are under attack.
Thanks, LJ.
Thanks a lot, everyone else. I appreciate
Thanks, everyone, for attending. Hope you
Bye,
had a
guys.
good time. Stay safe and stay healthy.
Thank you. Thank
You're
you.
welcome.